samples are kept absolutely pristine because we want to see things that were in space and not things that were on Earth. Again, a lot was learned during the Apollo era about doing that. And a couple numbers for you. It enters the box, the area of the Utah Proving Range at about 150,000 feet. The parachute's going to deploy at 16,400 feet. So
we just got the main parachute, looks like.
Okay, yeah, so we passed that flight level. And for comparison, the WB-57, we're seeing these images from is flying 45,000 feet. So that's why we're looking down on it.
Oh, wow. So it's below the aircraft now, below this high altitude aircraft. Wow. Let's listen in real fast here to some of the commentary from NASA TV, get some of their perspective.
Could potentially have a wonderful view momentarily as well. We'll continue to descend. Our next altitude descent will be at about 4,000 feet. Just a few minutes away from getting that sample from the other side of the solar system, from the surface of asteroid Bennu at site Nightingale to the rug. It looks like winds are relatively low. Not a lot of rocking back and forth. Those parachutes seem to be perfectly smooth coming down. Parachute there. Continuing to descend. The slight little bit of tilt back and forth of our SRC as it comes to its resting velocity of 11 miles per hour as it makes the final descent.
Tony, I can't help but notice that the surface of Utah, I can see now why they do so many space training missions out there, because it does almost look like the surface of the moon or the surface of Mars.
Arizona and Utah have been good to us in providing some great analogs for lunar or even Martian exploration.
I know it wasn't too long ago that they were taking the, forgive me, I can't think of the name of it, but the vehicle that the Artemis crew will be driving around on the lunar surface. They've been test driving it out there in the desert.
Yeah, they actually got a little space outside some of the main buildings of the Johnson Space Center too, where they do some of that.
We got about
I'm just blown away.
5 minutes here. Go ahead, Candace.
I was gonna say, I'm just blown away. We're going from like 27,500 miles an hour down to 11.
Yeah.
Like,
talk about like screeching brakes.
Right?
And you know what? This is relatively easy compared to, we talk about how these things inform other missions. Well, other missions have informed this as well. This is relatively easy compared to getting spacecraft down on Mars. Very, very similar challenges, but it's even more challenging there because the atmosphere is so thin. The parachutes have to be so much bigger, but it's the same thing. We got to slow down from 37,000 miles an hour down to basically zero, and do it without creating a crater in the process, without turning our precious spacecraft into parts strewn across the desert floor. So you're right. This is, most of that speed is being pulled off by the heat shield, and now the parachute. It's really not doing a whole lot of decelerating right now. The parachute's
doing. Got some comms here. We'll listen into real fast. Sorry, Tony.
That is phenomenal. Let's see that view here from that first helicopter. They've got visual on the sample return capsule under parachute. That orange creamsicle colored parachute, really bright in the morning light over the Utah Test and Training Range. A great view of the SRC.
All right, so we heard some radio communications, which I think were an indication that the helicopter now have some visual. Tony, your last comment made me think, is it easier to land on a planet like Mars that has less atmosphere, or is it easier to land on our planet, which might have more atmosphere, but we're more familiar with it?
It is significantly easier to land on the Earth than it is to land on Mars. Thin atmosphere means that there's enough there that you got to deal with it. The heating, the same kind of heating we see as we come into the Earth's atmosphere, this is an absolutely good test to show how that heating works. The same thing, it's friction, but there's so little that it's hard to really make a parachute work right. But the bigger thing is, and you pointed it out there, that we're more familiar with Earth, and we also can test things one-to-one on Earth. It's really hard to test something that's going to be landing on another planet because of the differences in gravity, because of the differences in the atmospheres.
Let's take a listen here again.
The team on the WB-57 doing
EDL milestone, we have touchdown. I repeat, EDL, SRC has touchdown.
And touchdown of the OSIRIS-REx sample return capsule. A journey of 1 billion miles to asteroid Bennu and back has come to an end, marking America's first sample return mission of its kind and opening a time capsule to our ancient solar system.
I loved Candace's reaction.
It's so cool!
Like a kid at Disney World.
Right?
There was
Like,
some
we
cheering.
just got Mickey Mouse to land in Utah, right? Like,
Right.
ah!
Yeah, here's the team. Here's their reaction. And you can see the team celebrating. You guys were talking about all the people, all the jobs that go into this. And this is probably even just then a small sliver of the amount of people who went into making a mission possible. You can see their celebration. Again, this is a mission that has been underway since the launch in 2016. And truthfully, it's been underway longer than that because of the amount of planning and construction and manufacturing that had to go in prior to the actual launch. So now we will watch as crews move on out there to where the capsule touched down to begin its recovery. You can see those military aircraft still in the sky, the ones that have been providing us the live images. And now the ground crews will take vehicles out there to try to collect this. And then, Tony, if my memory serves, they will hoist it onto a helicopter, I believe you said, to get it to their clean room. Is that right?
That's correct. And I'm judging from where that helicopter is right now, and it's not moved a whole lot, so it's probably pretty close to the landing site. And comparing it to the FAA submitted plan on where that proposed capsule landing area is, they hit pretty close to the center of that landing area. I'm sure we'll get some numbers eventually that talk about how far off they were, but I'm guessing it's going to be measured not in miles, but in feet.
And you mentioned earlier in our stream this morning that this morning, over the course of the last few days, they had the opportunity to make just small adjustments to their trajectory in space. And it's just amazing. It's like the butterfly effect, if anybody remembers that movie, right? Where you make just one small minor adjustment and then downstream, it would make a huge difference on where this thing would touch down on planet Earth. And they did it.
And that's one of the things that amazes me most about. There's people in that room that we just saw celebrating that were in part responsible for all that planning and the numbers and figuring out the right trajectory for the parent spacecraft to take to be able to eject it, the ejection process to make sure that it had the right energy to put it into the right descent path. And they did a fantastic, absolutely fantastic job. But keep in mind too, that all that planning, it isn't just numbers that once you figure it out, that's the way it's going to go. There's variables that happen beyond there, not the least of which is our atmosphere. Our atmosphere is incredibly variable, not just the weather, but the upper parts of the atmosphere. It's very, very lumpy. So we just don't know where that thing is going to go until it goes. And that's why those landing areas are sometimes 50 miles across.
It looks like another helicopter.